Hey everyone, welcome back to the show. Today we're diving into a paper that's making waves in the computer vision world.
It's called A Polynomial Formula for the Perspective 4 Points Problem.
Catchy title, right?
Definitely grabs your attention. But don't worry, we're here to break it down and make sure it all makes sense.
All right, so let's start with the basics. What's this perspective 4 points problem all about?
Well, it's all about figuring out where a camera is in 3D space.
Oh, like if I take a picture with my phone.
Exactly. You've got a 2D image, but how do you determine the camera's position and orientation in the 3D world? That's the challenge.
I see. And this paper focuses on using 4 points to solve this problem.
Precisely. It's a specific case of the more general perspective endpoint problem, or PMP, where n can be any number of points.
Okay, so what makes this paper so special? Is it just a slightly better way to solve P4P, or is there something more groundbreaking going on?
Oh, this is far from incremental. It's a whole new way of thinking about P4P using some pretty elegant math.
Intrigued. Tell me more.
The key is that P4P is what we call overdetermined.
Overdetermined.
Yeah. It means we have more information than we strictly need to find a solution.
That sounds like it could make things more complicated.
It can, but it also opens up some interesting possibilities, and that's where the polynomials come in.
Polynomials, like back in high school algebra.
Yep, those guys. But they're not as scary as they might seem. The authors of this paper realized they could use polynomials to represent the relationships between the 3D points and their corresponding 2D projections in the image.
Okay, I'm starting to see the connection. So how does that actually work?
Well, they focus on two key things.
Yeah.
First, the squared distances between the 3D points.
Got it.
And second, they use something called dot products between the 2D points in the image.
Wait, hold on. Dot products, remind me what those are again?
Think of it like this. You're shining a flashlight on a surface. The dot product measures how directly the light hits that surface.
Okay. So a bigger dot product means a more direct hit.
Exactly. And in this case, we're using dot products to analyze the geometric relationships between the 2D points in the image.
I'm following so far. So we've got these distances and dot products. And then what?
That's where the real magic happens. They derive polynomial equations that capture the essence of the P4P problem in a much more compact and elegant form.
Polynomial equations, huh? Sounds a bit complicated.
It is. But the beauty is that these equations lead to something called key polynomials.
And polynomials. Those sound like something out of a martial arts movie.
Maybe, haha. But in this context, they're the key to unlocking a fast and accurate solution to the P4P problem.
Okay, I'm all ears. How do these key polynomials work their magic?
Well, first you use them to generate a set of possible solutions. Think of it like narrowing down the possibilities.
Right.
Then you have to figure out which one of those solutions best fits the data you have. It's like finding the perfect puzzle piece.
And
Finally, you have to make some adjustments to account for the original camera orientation. Remember, that's what we're ultimately trying to find.
right, so we're using these key polynomials to sift through the possibilities and pinpoint the most likely location and orientation of the camera.
Exactly. And the best part is this method is much faster and more accurate than traditional P4P approaches.
Okay, I'm starting to see why this is causing such a buzz. But can we see this in action? Like a real-world example?
Absolutely. The paper has a great example using a specific set of 3D points and their corresponding 2D points in an image.
So they show how the key polynomials actually work to determine the camera's position.
Precisely. It's a fantastic way to see the math come to life.
So we've explored the problem, the aha moment, the algebra behind it, and even met the cheese.
We've covered a lot of ground.
But before we jump ahead to the novel notions section, let's take a step back. Why should our listeners care about all this? What's the real-world impact of this polynomial wizardry?
That's a great question. To understand the impact, we need to think about the bigger picture. P4P is a fundamental problem in computer vision.
Right. It's everywhere. Robotics, self-driving cars, augmented reality. They all rely on accurately understanding 3D space from 2D images.
Exactly. And if this method is faster and more robust, it could lead to some major advances in all those areas.
That's pretty exciting.
Yeah.
So this paper has the potential to make computer vision algorithms that use P4P much more efficient and accurate.
It does. And it also opens up new avenues for research, which brings us to our novel notions segment.
Oh, yeah, that's where we get to explore some of the crazy possibilities this research has inspired.
The fun part.
But we'll save that for part 2 of our deep dive.
Okay, so we've established this polynomial approach. It's pretty amazing. But let's take it a step further.
Yeah, let's get those creative juices flowing.
Yeah.
What kind of novel notions has this research sparked for you?
Well, one thought that keeps popping up is real-time high-accuracy P4P solvers. Imagine the possibilities for things like augmented reality.
Augmented reality.
Okay, and let's...
Picture this. You're wearing AR glasses, and the experience is completely seamless. No lag, no jitters, because the device can instantly and precisely determine its position in 3D space.
That sounds incredible.
Yeah.
But how realistic is that? We've talked about how computationally demanding P4P can be. That's where the brilliance of this polynomial approach comes in. Remember how we talked about its speed? Traditional methods can be slow and clunky, but this approach is like a shortcut. It gets you to the solution much faster.
So not just accurate, but efficient, too.
Exactly. And when you consider modern hardware with parallel processing capabilities, the speed gains could be even more dramatic.
Plus, it can handle noisy data, so it's robust.
Precisely. It's built for the real world.
But aren't there already real-time P4P algorithms out there?
There are, but many rely on approximations or are designed for specific scenarios. What's exciting about this polynomial approach is its potential combination of speed accuracy and generality. It could really shake things up.
It's like a whole new toolbox for tackling P4P and maybe even more complex problems in the future.
Speaking of more complex problems, that leads me to my second novel notion.
Okay, this is where things get really interesting.
What if, and this is a bit speculative, but what if we could develop similar polynomial-based solutions for PNP problems with more than 4 points?
More than 4 points, like P5P, P6P,
Yeah.
even PNP with a really big N.
Exactly. Right now, most solutions for larger n rely on iterative methods that get really complicated and computationally expensive as n grows.
Yeah, I can imagine.
But if we could find polynomial solutions for those cases, it would be a game changer for pose estimation.
Okay, my mind is officially blown,
Yeah.
but isn't that a huge leap? Going from P4P to a generalized solution for PNP sounds incredibly challenging.
It is a challenge, but I don't think it's impossible. This success with P4P gives us a starting point. If we can figure out the underlying mathematical principles that make these polynomial solutions work, we might be able to extend those principles to more complex scenarios.
So it's a long shot, but the potential payoff is enormous.
Exactly. The speed and efficiency gains could be revolutionary. It would be like finding a universal key that unlocks a whole new level of understanding in computer vision.
Okay, I'm on board with this polynomial revolution, but let's be realistic for a moment. These are just novel notions, right?
You're absolutely right. We're in the realm of speculation here. There's no guarantee these ideas will pan out, and there will be challenges along the way.
Right. No polynomial-powered flying cars just yet.
But it's this kind of exploration that drives scientific progress. And who knows, maybe one of our listeners will be inspired to take on these challenges and push the boundaries of what's possible. That's what makes research so exciting, the constant pursuit of the unknown.
So we've explored this new polynomial approach to the perspective 4-point problem.
And we've even ventured into some pretty exciting novel notions about where this research could lead.
It's been quite a journey.
Yeah, it has.
But let's bring it back down to earth for a moment. What about the practical implications? Where could this research actually make a difference in the real world?
That's a great point. It's easy to get caught up in the theoretical stuff, but the real impact comes when these breakthroughs translate into real-world benefits.
Exactly. So besides the obvious applications in robotics and AR, where else could this polynomial approach have an impact?
Well, one area that comes to mind is medical imaging.
Medical imaging?
Yeah, think about it. Surgeons could use this technology to precisely target tumors during surgery.
Wow, that would be incredible.
Or radiologists could get even more accurate 3D reconstructions from medical scans.
That's amazing. What about other areas of science? Could this approach be useful in fields like astronomy or microscopy?
Absolutely. Astronomers could use it to map the structure of distant galaxies, or biologists could study the intricate details of cells.
So it's not just about computer vision. It has the potential to impact a wide range of scientific fields.
Exactly. This polynomial approach could give scientists in various disciplines faster, more accurate, and more robust tools to analyze complex 3D data.
Let's not forget about the potential impact on artificial intelligence.
Yeah.
If we can teach machines to understand 3D space from 2D images more effectively.
It could revolutionize things like object recognition, scene understanding, and even robot manipulation.
So this paper really is more than just solving one specific problem.
It's about challenging us to think differently about computer vision. It's like we've been given a new lens to view the world, and the possibilities are endless.
I can't wait to see what future research builds upon this foundation. Maybe we'll have a whole new set of novel notions to discuss in a year or two.
It's exciting to think about.
Well, I think it's time to wrap up this deep dive. We've covered a lot of ground today, from the nitty-gritty details of the polynomial approach to its potential impact on various fields.
Hopefully, our listeners have a better understanding of this groundbreaking research and its implications for the future of computer vision.
And if you're eager to delve deeper into the math, don't forget to check out the link to the full paper in the show notes.
Keep exploring and let your curiosity guide you.
That's all for today, folks. Until next time, when we'll dive into another fascinating corner of the machine learning universe. Keep those algorithms humming.